Hi, we're going to look at how to use the Boltzmann distribution to find the heat capacity of a simple system. We're going to look at, imagine a solid with number of particles n. Now, I'm going to think about each particle in a solid as having two energy levels. Now let them be, let's say one of them is minus E, the other level is E. And I imagine that of these particles, these n particles, and one of them is in the lower level and two of them is in the higher level. Now to make this a bit less abstract, a possible example of such a system would be, say, a salt that is paramagnetic. Now what that means is that this salt would contain ions, certain ions. So ions are particles of atoms that has either lost or gained some charge. So this kind of salt will contain ions that have magnetic moments. So each ion would be like a tiny magnet. And when this ion is in a magnetic field, it can either align its little magnet along the magnetic field or in the opposite direction. And these two possible directions means that it can either have a lower energy or a higher energy, alright, depending on whether it's aligned with the field or if it opposes the field. So this is an example of a real life solid that can show such a type of energy levels. Okay, and what I'm going to do then is to consider this system and to see how we can use the Boltzmann distribution to derive the heat capacity, and in doing so to understand what goes on in the energy levels, and to understand how this microscopic theory of statistical mechanics, how this allows us to explain the thermodynamic properties of a big solid object, properties such as the heat, the entropy, and the heat capacity. So let's start. Now let's start by writing down the Boltzmann distribution. N1 would be A exp. Now the formula is minus of energy over kT. Now in this case, for N1 the energy is minus epsilon, so I have minus of minus epsilon, which is plus epsilon over k Dt, and N2 would be A exp minus epsilon over k Dt. So I have these values for N1 and N2. Now in the next step, towards finding the heat capacity, we would want to first find the total energy. Now we know that the total energy we can find by multiplying the number of atoms or ions in each level by the energy. But before we actually do this, we have the unknown A, and we really need to find A first. So we should do that. Now we'll find A by using, if you recall from the last session, the relation between the number of particles and N1 and N2. We can find A by substituting into this expression. So A is equal to, N is equal to, N1 will be A times exponential of E over KB T, and 2 A exponential of minus E over KB T. So then we can, so A is a common factor, we can factor it out and solve for A. So A would be equal to N over this expression. So this will be exp epsilon over kb t plus exp minus epsilon over kb t. Right, now clearly it's going to get cumbersome if we keep writing out these exponential expressions, which all looks pretty much the same. So that's a common way to simplify the writing. Now, this term here, this exponential with the e over kt, okay, this bit here, is often called the Boltzmann factor. So that's the Boltzmann factor, just the exponential bit. And at the bottom of this denominator for A, you can see that it is just a sum of all the possible Boltzmann factors. Alright, the Boltzmann factors with all the possible energy levels. If I have more levels, I'll have more terms. So it's a sum of the Boltzmann factors, and the symbol that is often used to represent the sum, represent this sum, is Z. So if you look at books on statistical mechanics, you'll see Z quite often, and they call it the partition function. Right, Z is the sum of Boltzmann factors. So I'm just going to make use of that for now. Right, so now that we have solved for A, we have the full formula for N1 and N2, and we are ready to find the total energy U. Okay. U is equal to N1 epsilon 1 plus N2 epsilon 2. Right. Okay. Then N1, as we recall, is A exp epsilon over k b t. Remember that there isn't a minus sign because the energy level is minus epsilon, and that's epsilon 1, so which is minus epsilon, right? So that's what we have. And N2 is A E x p minus epsilon over k b t, and E2 is epsilon. So that's that, right? Now notice that there are common factors A epsilon down here. So in principle, we have already seen the expression for A just now. We can just substitute that expression into A, and that's it, that's the answer. But what I'm going to do now is I'm going to simplify this expression find some way to do that. So, okay, I'm going to factor out the A and epsilon. Now actually I'm going to factor out minus A epsilon. Right, so I have exp minus sign there. So that. And now I'm going to plug in the expression for A. If you recall, A is equal to n over z, the sum of Boltzmann factors. So I'm going to substitute this into here. Right. So I would have a factor of n, and I would have to divide the whole lot by the z, which is the sum of the partition functions. So it's going to be complicated. Exp of that minus exp of that Alright, and the partition function will be the sum of the Boltzmann factors. Alright, so we have this complicated expression here for U. Now, if you look at this, you might recall that this looks the same as the expression for the hyperbolic tangent. Clean that off. So this is the U that we have. Now the hyperbolic tangent, let's see, let me write it here, is TANH of x, right, that's equal to e to the power of x minus e to the power of minus x divided by e to the power of x plus e to the power of minus x. So that's the formula for the hyperbolic tangent. Now if you compare that with that, you see the exponential minus exponential, like that. You see the arguments have opposite signs, the minus sign there, like that. So clearly this is just a hyperbolic tangent. Therefore, we have U is equal to minus n epsilon and hyperbolic tangent of this argument here. Then we have a much simpler expression now. So now that we have a formula for U, we can easily find the heat capacity by differentiating this. So if you differentiate this, you have to differentiate with respect to the temperature to find the heat capacity. So differentiating the hyperbolic tangent gives you the square of the hyperbolic second, and so on and so on. So I shan't go through that. Instead, what I'll do is I'll look at some graphs. I'll try to sketch some graphs to see how these total energy and the heat capacity and also entropy, how these thermodynamic quantities vary with temperature, so we can have a better understanding of the overall physics of this solid. So the next thing I'd like to do is to sketch a graph of total energy U against temperature T. Right. U and that's T. So in graph sketching, it helps if you are familiar with the common, the shape of graphs for common functions. Now the hyperbolic tangent has a graph that you can find in textbooks, but in this case that might not be very helpful because we are not actually plotting U against the argument of the hyperbolic tangent. That means against the whole of that thing that we are plotting against, we want to plot against the temperature which is in the denominator. So that makes things a little more tricky because when the denominator T gets small, the argument actually gets big. So it goes in the opposite way. So what we are going to do is this. We are going to try to calculate U as T goes to 0, becomes very small, and or as T becomes very big, as it goes to infinity. So as T goes to 0, let's see what happens to U. Now if T goes to 0, then E over T goes to infinity. And the hyperbolic tangent of infinity is 1. Therefore, U is just minus NE. Alright, we have one answer. And what happens for very large T? As T becomes very large, E over T goes to 0. And the hyperbolic tangent of 0 is 0. U goes to 0. So we have 2 points for the graph. Sort of. When T goes to 0, U goes to minus NE. We have 1 point there. When T goes to infinity, that way U goes to 0. So it sort of goes to there. Now the obvious thing to do is to just draw a curve joining those 2 points. That's simple enough. But there's just one little detail which can be important, which is the gradient of the graph. It might go from there to there, but it might just not go in a direct curve. It might twist and turn a little bit. And an important thing that we need to know, that we need about this particular system, is the gradients of the curve for U, particularly at t equal to 0. Now the reason why gradient is important is simply because the gradient of U, if you recall, with respect to T, is the heat capacity which we want to find. So it's important to get the gradient right, and it turns out that as T goes to 0, the gradient of U actually goes to 0. If you differentiate this, alright, you'll get an expression after you differentiate the hyperbolic tangent, and you find that when t goes to 0, du dt would go to 0. So I shan't go through all the algebra, but I'm just going to use that as a given knowledge. So I would expect that when I plot the graph, I should show that the graph starts off horizontal from t equals to 0. It should start off horizontal and then it will curve upwards and then eventually tend to 0 as t goes to infinity. So the graph should really look like this. Horizontal, go up, tend to 0. So that was wrong. This is the correct curve. So it's important to get these features right when you plot a graph, right? The important things about a graph are some main points that you know it crosses, and some of the main gradients where it should be horizontal and it should not. That's the curve for U. Now that we have a graph for U, we can next sketch the curve for the heat capacity, C, using the knowledge that C is the gradient of U. So let's start. Let's start from t equal to 0. At t equal to 0, as we have already seen, the gradient is 0. It starts horizontal. So, which means that C is 0. Now, as temperature increases, U increases. And you see that the slope increases. Slope increases. So C increases. Now, but at some point, the slope turns back and starts decreasing as U tends towards 0. So at some point, C reaches a maximum, turn back and start decreasing. And as U tends towards 0, the curve gets flatter. So the gradient gets closer to 0. So C comes down and approach 0. And that is the curve for C. Just a simple curve with a peak. Now this simple curve contains a feature that is very unusual. It contains a peak. Why is a peak unusual? It is because for the heat capacity of materials, whether it is a gas or solid or liquid, heat capacity almost always increases with temperature. In most cases and for most substances, as we'll see in subsequent lectures. And it is only for this very special example in which we have two energy levels, and which happens with, for example, paramagnetic salts, substances with magnetic ions. It's only for this very specific example where we have a situation that the heat capacity has a peak, meaning that it goes up and comes down again. Alright, as I said, for most situations and materials, the heat capacity almost always keep going up. It might flatten off at some value, but it would very seldom come down again. So because of this unusual feature in this kind of system, this peak has a name. It is called the Schottky anomaly. Try to spell that. S-C-H-O-T-T-K-Y. The Schottky anomaly. That's the peak of the heat capacity. So now we have a fair knowledge of the behavior, or you can call it the physics of the system. Alright, we know how U and C behaves. Now there is one more thermodynamic quantity which we will need in later on in this course, and that is entropy. So in principle, we could derive the entropy either using formulas from thermodynamics, using the U here, or by using the Boltzmann postulate for entropy and making use of the Boltzmann distribution formula. But we're not going to do that, right? It's possible. Algebra is quite involved. We are going to do it. We are going to try and sketch a curve of the entropy with respect to temperature to get an idea of how it varies. And we are going to do it by looking at specific temperatures and try to understand what happens at very low and very high temperatures, and see if we can calculate the entropy for this high and low temperature limits in a simple way. Right. So the idea is this: we have these two levels. We have n particles, and we're interested in entropy. Alright? And I want to know how it varies with temperature. What does the graph look like? And I'll start by thinking about what happens when T goes to 0. But we also need a formula for the entropy, and I'm going to use the Boltzmann postulate. Right, entropy is Kb times log of the number of possible arrangements of the particles. That's the lower level is minus epsilon, higher level is epsilon in this example. So, in order to use this formula, I need to know the number of arrangements of the particles among the two levels when T goes to 0. So what happens when T goes to 0? When T goes to 0, all the particles go to the lower level. Right? Now, that would seem obvious if you are familiar with quantum mechanics and energy levels. Now, but we have to be careful here, because we have just derived the Boltzmann distribution, and the important thing in this reasoning is that we should logically relate these steps to the Boltzmann distribution. So let's also have a look at the Boltzmann distribution and make sure that we are doing the right thing. So we have n1 and n2. The expressions are a exp e over k dt a exp minus e over k dt. So what happens to these expressions when t goes to 0? Let's see. When t goes to 0, since t is in the denominator, the argument goes to infinity. So it looks like n1 goes to infinity. What does that mean? Now when t goes to 0 for the next level, for n2, the argument goes to minus infinity because there's a minus sign there. So e to the power minus infinity goes to 0. So this goes to 0. Now we have a situation here. n1 goes to infinity, n2 goes to 0. Now we can understand what n2 going to 0 means. It means that there are no particles at the higher level. But what does n1 going to infinity mean? Surely we have a fixed number n of particles. We don't have an infinite number of particles. Does this mean that that n number of particles become infinite? No, that's physically not possible. If we are just having a fixed number of particles, we want to cool it down to 0 temperature. So what this means is that we have to look at these two results as a mathematical ratio. So we have a ratio of a certain number to a certain number. Alright, the ratio of these two numbers. And as temperature goes to 0, the ratio of n2 to n1 goes to 0. So we should just look at this ratio and understand that the number of particles at the higher level goes to 0, and that means that all the particle goes to the ground state. Right, which means that we really don't have to worry about the fact that n1 goes to infinity in this formula here. So this also means that although we have formulas for the Boltzmann distribution, we have to be careful and we have to think in terms of a physical picture when we actually use and interpret the results of the formula. Okay, so when t goes to 0, we have n. We have n2 at the higher level going to 0, no more particles at the higher level, and n1 therefore goes to n. So all n particles go to the ground state. Right. So we have this. What does this mean? What does this mean about the entropy? Now we need to find the number of arrangements, and you remember the formula for, there's a formula for the number of arrangements in terms of factorials of these numbers. But if you look at this, we don't really need that formula to find the number of arrangements, because if all the particles are in the lower level, there is only one arrangement. Alright, you have more arrangements only if there are also particles in the top level and you can switch particles around and then you can get different arrangements. But if all particles are at the lowest level, that's the arrangement. That's it. So there's only one arrangement, and if there's only one arrangement, then log of 1 is 0. So therefore, S is 0. So now we have a value for S. At 0 temperature, entropy is 0. So we have found the first point on the graph. Now let's find the next point when t becomes very large, when it goes to infinity. Let me when t becomes very large, what happens to the particles? Now it is tempting to think that because when t becomes very small, all the particle goes to the lowest level, therefore the opposite happens when t becomes very large. So when t becomes very large, all the particles should go to the higher level. Now that is wrong. That is wrong because it doesn't agree with the Boltzmann distribution. Now let's see why that is wrong. Let's look at this Boltzmann distribution. if t goes to infinity, for n1, the argument here, when t goes to infinity, becomes 0. Alright, e over infinity is 0. So exponential of 0 is 1. So therefore that becomes 1 and n1 goes to a. Now n2. Likewise, when t goes to infinity, e over t becomes 0. So likewise, exponential of 0 is 1 and we have just a here. So what we have is n1 goes to a, n2 goes to the same number. And that means that there will be the same number of particles in both levels. So how do we reconcile this with the idea that if temperature becomes very high, the particles do not all go to the highest level? But there are actually two things to think about here to try to understand this. One thing is this, is to understand why the Boltzmann distribution gives equal amounts in both levels. If you look at the exponential, you see that as t becomes very big, e over t becomes very small. So it's because the e here sort of corresponds to the spacing between the two levels. It's because this spacing becomes very small compared to kBt. Alright? So at very high temperature, the average energy of the particles are also very high. And as far as the particles are concerned, the energy difference between the two levels is quite negligible. So therefore, it becomes equally likely for it to occupy either level. Alright? Because for the particle, there is hardly any difference between the two levels. And that is why the particle would be equally likely to occupy either level, and we end up with equal population for the two levels. So that's the understanding we can get from looking at the Boltzmann distribution. Now the other thing is this. Surely you might think that if the temperature is very high, we are putting in more and more energy. So surely if we put in enough energy, we can pump all the particles up to the top level. That's true if you are able to put in that much energy. But the thing is, when we have a temperature T, we have a situation in which this system is in contact with a surrounding which has this very high temperature. So we have a situation where this system is in equilibrium with a surrounding temperature. And in this situation, you're not actually pumping in as much energy as you like. You are really allowing this, the energy gained by this system or solid to reach an amount, alright, in which it becomes in thermal equilibrium with the surrounding. And because of this situation, you don't actually pump in as much as you like. It's determined by this equilibrium situation. And therefore, you just can't get more particles up into the higher level. Alright, you can't get the higher level to have more particles than the bottom. So that's the reason for this. And just as an aside, what if there is some way of pumping in more energy? Or is there some way of pumping in more energy? In fact, there is. That's what happens, for example, in things like lasers. It's something called population inversion, in which you use special techniques. Like, for example, in laser, you use optical or some very bright light to force more energy into the higher level, to the extent that you get more particles in the higher level than at the lower level. And that's called a population inversion. It doesn't happen just by putting this object next to a very hot surrounding. Alright? It happens when you use a special method to pump in the energy. And if that happens, then you can have more particles on top. Now, but that also means something about the Boltzmann distribution, because the Boltzmann distribution as it is, alright, because of the nature of this exponential, it would always get smaller when the energy gets higher because of the negative sign here. So what this means is that as far as the Boltzmann distribution is concerned, if you use this special method to pump in more energy and to get more particles at a higher level, the Boltzmann distribution, the idea about the Boltzmann distribution has to be modified. It will only work if you now take t to be negative. Because if you don't, then you still have the minus sign, and this Boltzmann factor has to decrease when E increases. Only if you change the temperature T to a negative number, then you end up with minus of a negative number, which is a positive number, and only then would the exponential increase with energy. So which means that if you are able to pump in more energy and increase the population at a higher level, then we describe this situation by using negative temperature. Alright, so that's the aside. Now coming back to this, we need to find what happens now when t goes to infinity. And we have seen that n1 and n2 goes to the same value. So, right, and we have n1, so n1 goes to, so if there's the same number in both levels, that means that n is split into half and half. So n1 goes to n over 2, and 2 goes to n over 2. Okay, now it looks like now that we have n1 and n2, we can use this to calculate omega, because after all, we know the formula for omega. If you recall, omega is equal to n factorial divided by n1 factorial, n2 factorial. So we could actually use that. But in this case, there's actually a simpler way to do it, because if you think about what I said just now, that it is equally likely for a particle at such a high temperature, is equally likely for a particle to occupy either level, then that means that for each particle, there are two possible arrangements. So if there are two possible arrangements for each particle, then for two particles, the total number of arrangements would just be 2 times 2. And if you have n particles, it would be 2 times 2 times 2 and so on until you have n factors of 2. In other words, 2 to the power of n. So, therefore the number of arrangements is just 2 to the power of n. So this gives us a much simpler expression. Let me write that down. I can simplify that a little bit by bringing the n down as a factor. So n kb log 2. So that, which means that at very high temperatures, the entropy should approach this value. So now I can plot the graph. Starting from 0, the graph should go up and it should tend towards this n kb log 2 value of the entropy. Okay, we'll stop here.